Hello and welcome to the second part of the reactions of halogenoalkanes. Previously looked at nucleophilic substitution. In this video we're going to look at elimination. So just a very quick recap. If we start with halogenoalkanes, that's any alkane where one of the hydrogens has been substituted by a halogen, which I'm going to use X here to represent. We can have a nucleophilic substitution reaction happen. And our common nucleophiles are going to be OH minus ions are going to be aqueous. We're going to have our cyanide ions and we're going to have our ammonia. Okay, and what that's usually going to end up in producing is we switch it out and we're going to end up with C4H9OH. C4H9, and then we're going to have this CN group somewhere attached, so on the ends, coming off where that was, so that's your nitrile, and then we're going to have C4H9NH2. So that's my substitution sort of reaction. As I said today, we're going to be looking at something slightly different. This is going to be our elimination. And this is going to result in an unsaturated molecule. Okay, and we're going to look at this in depth, so you're going to end up with an alkene. Okay, and so actually what we have is this interesting sort of elimination reaction, and we're just going to talk about, well, what is it that causes this to happen. So one of the early things I'm going to look at is conditions, and I'd like to just discuss this. This is clearly stated in the AQA specification, so you do need to know these, okay? So the first thing is that you're going to have your reagent. Now your reagent is going to be sort of KOH maybe, so a hydroxide, okay, any hydroxide, and it is likely to be quite a high concentration. So we're going to have this high concentration hydroxide. We're going to have no water, so this is going to be, and this is quite a useful word, so it's going to be ethanolic, which just means dissolved in ethanol. It's going to be ethanolic, it's going to be dissolved in ethanol. And last thing is that it is going to be hot. So we're going to increase the temperature, increase the concentration, we're going to put our potassium hydroxide in, we're going to dissolve it in ethanol. And what this means is that we're going to end up with a elimination reaction taking place. So how does this differ from the nucleophilic substitution? Because you'll notice if we're using this and we're really focused on this hydroxide, remember the reason I said potassium is a reagent is a named compound that contains the part that we want to react. That hydroxide also exists over here, so can result in substitution as well. So it's change in conditions, and actually here what we're going to see is that the OH minus acts as a base, not a nucleophile. And we're going to look at a couple of examples of this for primary, secondary and tertiary alcohols. For the sake of this video, we're going to look at primary, secondary and tertiary halogenoalkanes. I'm going to use the same molecular formula, this C4H9X for each one. and we'll just look at how the mechanism can be applied for those. So I'm going to start off with, and let's say we're going to look at primary halogenoalkanes. This is going to be our starting point. Now, as I said, I'm going to do this. I'm going to go, let's put the chain down here, like C, 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 C. I'm going to put my halogen on. I'm just going to use X to represent my halogen. I'm going to use blue to highlight a specific hydrogen. And then, just for the clarity of the video, I'm just going to leave these bonds open so you can see where the other hydrogens would be. Okay, so this would be all your hydrogens. This is my hydrogen on this carbon that I'm going to be looking at. This is my halogen atom, and I'm just going to put my OH minus over here. I'm going to go O, I'm going to put my H to this side, okay, and it's got a negative charge. Now what we have over here is that our hydroxide ion is going to act as a base, not as a nucleophile. And actually what it's going to do as a result of that is it's going to attack the hydrogen of a neighbouring carbon to the CX bond. Now we might describe this as your alpha carbon, so it'd be a neighbouring carbon or a beta carbon, so it'd be a beta hydrogen. You might see this terminology in other places. So we can see here's my CX bond. This is the neighbouring carbon, it's directly next to it. This is one of its hydrogens. And the lone pair here is going to come across and attack that hydrogen. As a result of this, the electrons from this hydrogen are going to fall back into the bond here, between the CX carbon and the neighboured carbon. And again, in turn of that, the extra electron density here repels these electrons and it comes up to the CX bond. So, as a result, what we're going to end up with is the production of the following compound. You're going to have your carbon here. We're going to have, right, let me draw out the original carbon chain as was. I'm going to come up to here for a second like this. Okay, nothing has changed on this carbon, nothing has changed on this carbon. This carbon has lost the hydrogen there, this carbon has lost the X there, so I'm just going to do this. And that double bond, I'm just going to do here this colour. You can see that double bond is formed there. And then we're going to have alongside this, we're going to have H2O, which is from the hydrogen and the hydroxide, and we're going to have X minus. Now remember, in this case, if we had potassium hydroxide, we might also just put in as KX, so that we have potassium halide. Okay, so the constituent ion to this is going to be from whatever our reagent was. The hydroxide from the reagent will make water, and then you're going to end up with your alkene. And if we just wanted to practice naming this, this is going to be bute 1-ene, and there's going to be no EZ isomerism because it's on the first carbon and it's got those two hydrogens present there. So it's pretty straightforward for a primary halogenoalkane, and this is primary because the carbon from the carbon to halogen bond has only got a single carbon attached to it, so it's only got one neighbour, so it is a primary halogenoalkane. We're now going to look at what happens if we use a secondary halogenoalkane. Now, I've done this in 2 steps, and we're going to sort of explain why, or 2 versions. But I just want to look at this, and just to point out that what we are looking at here, same molecular formula, positional isomerism, we're looking at bute 2, sorry, absolutely naming that wrong, aren't I? We're looking at 2 halogenoalkanes. butane. So that could be 2-chloro, 2-bromo, and it's called that because our halogen is on the second carbon to give us the lowest number. Now, the reason I've drawn this twice and I've got different colours is because if we think of our original rule, we said the hydroxide will act as a base and it will react with a hydrogen on a neighbouring carbon. Now, in this case, we've got two neighbouring carbons. We've got this one here is a neighbour to the CX bond, and this one here is a neighbour to the CX bond. And so what I'm going to do is I'm going to follow through the mechanism for each of those neighbours separately, because it could happen on either. So let's go for this one here on the left. What we're going to have, the hydroxide, it's going to act as a base, it's going to attack the hydrogen on that neighbouring carbon. The electrons from the carbon to hydrogen bond are going to fall back into that carbon to carbon bond, and this is going to repel the electrons in the carbon to halogen bond up to there. And so what you're going to result in is you're going to have that carbon there, that bond, that carbon there. Then we've got this side, that carbon, nothing has changed, and that carbon, nothing has changed. And so when we look at this, let's fill in our hydrogens, nothing's changed here, nothing's changed here. Here it's lost the hydrogen, the halogen, so I'm going to put this down here. This side, it's lost one of its hydrogens, so it's got two. I'm going to draw my double bond in like this. And again, if we look at that, because it's on the first carbon, so this is going to be but1ene. Because it's on the first carbon and these are both hydrogen, there is no opportunity for EZ isomerism, geometrical isomerism, to occur. Alternatively, if we look at this side, I'm going to go through the same process. Hydroxide acts as a base, it attacks the hydrogen on neighbouring carbons. So here's my CX bond, this time we're going for the pink neighbour. When this happens, the electrons from the carbon to hydrogen bond go to the bond between that carbon and the carbon to halogen. This extra electron density repels the electrons from this bond to the halogen, producing a halide ion, which I didn't draw on this side actually, so I should be less lazy and put in all of my substances. Okay, so this happens. Now again, if I draw this out, I'm now going to go, there's this first carbon, I'm going to go to the second carbon, comes across to my third carbon here. I'm going to put in my double bond. I think this might be a better order of drawing it. So I put in my double bond. Now look at what else has changed. This has lost the halogen, so it's still got one hydrogen left, so I'm going to put that down there. Nothing has changed on this one. This has lost one of its hydrogens, it's still got a remaining hydrogen, and nothing has changed on this one. So here you can see immediately that both sides have got 1, 2 groups on, 1, 2 groups on. Okay, so actually I might get an alternative product where the orientation is a little bit different, and I could have my CH3 up here, so my carbon, my hydrogen, I have my double bond as I had before, and this time just going to flip over these two, so I've got my CH3 down here. Now if we look at those, what I've now got is this one there on the same side, so this is going to be my Z isomer, and here they're on opposite sides, so they must be enemies, and it is my E isomer. I get around to naming them. This one is going to be, well, the alkene's on the second, so it's going to be but because it's still 4. It's going to be 2-ene. I'm going to include this classification, so it's going to be Z but 2-ene. This side is going to be E but 2-ene. And so actually when we have a secondary halogenoalkane, we end up with 3 products: but1ene, but2ene, but with 2 geometrical isomers. You may find that you have a secondary halogenoalkane where it is symmetrical. So if this had been pent and I'd have another carbon on this side, then you wouldn't get the positional isomerism, because no matter which side it fell, the double bond would be situated on the same number carbon. However, you would still potentially get the EZ isomerism. So with this, my advice would be to always draw out all of your possible products. This is quite a nice way of doing it. Just being aware of which carbon you're looking at, and then working out what the products are. And then just make sure they're not imposable on each other. You can't flip it and place it to the same place. Last but not least, let's look at our tertiary halogenoalkanes. Okay, so again, I've drawn it out here. Now, the secondary one was when the base carbon from the CX bond had 2 carbons attached. We now have 3, so it's now a tertiary halogenoalkane. You can tell it's tertiary. There are no hydrogens directly attached to the carbon to halogen carbon. So this is our tertiary structure. I'm using the same molecular formula, so this would be 2 halogeno, and then we don't need a number for the methyl group because it can't be anywhere else. Methyl propane. This is still the same molecular formula, and that's why I've chosen to use it. I'm going to have my hydroxide ion down here. And again, mechanism very, very similar. So what's going to happen is the hydroxide ion acts as a base. It attacks a hydrogen on a neighbouring carbon. Now the reason I'm only doing 1 is because each of my neighbouring carbon groups are identical. If I had different length chains, then I would want to do this for every single potentiality. So I'd want to do 1 on this chain, 1 on the second chain, 1 on the third chain, if they were all of different lengths, and would therefore produce different products. So this is going to happen here. I'm sure you can see where this is going. Electrons here fall back into that bond, and this creates enough repulsion for the electrons here to come to my halogen. So what I'm going to produce, we'll draw it out. I'm going to start with here. Now you're going to have my single bond to that carbon. It's going to have the extra electrons that fell into it. This is going to have its 2 hydrogens attached. And this one is going to have CH3 and CH3. Okay. When we do this, it is the exact same process. You're going to still have your halide ion. You're still going to have some water produced. Okay. And we're going to have that double bond. Now in this case, what we've got is we've got 2 methyl pro 1 ene. So here's my first carbon, second carbon, it's got a methyl group, third one. Now we have to just bear in mind that with this it can produce positional isomers if the chain is asymmetrical. So if the chain here, if we had an extra carbon here, then it could have gone that way or that way, so you get a positional isomer. So if the halogenoalkane is, I always struggle with spelling this word, so asymmetrical, it just always feels like it's got too many letters, but if it's asymmetrical, you can do that. And again, potentially depending on what you've got coming off, if your carbon chains are longer than a single carbon, it can lead to EZ or geometrical isomerism. And that's something definitely worth looking into. Now I know we've spoken about these, primary, secondary and tertiary halogenoalkanes, and I just wanted to point out that actually when you have these in this kind of process, what you're likely to find is that a primary halogenoalkane is more likely to undergo nucleophilic substitution. Doesn't mean it can't do the elimination, but it's more likely to do nucleophilic substitution. Secondary halogenoalkane is more likely to, well, it's going to do a mixture of both, mixture of nucleophilic sub and elimination. Okay, and then the tertiary one has a prevalence to elimination. Okay, so dependent on what you've got, you're going to be more likely to have these processes take place. Hopefully that's been reasonably useful. I would take the time to go through, draw up a generic mechanism diagram and practice applying that mechanism to a range of halogenoalkanes to produce a range of different alkenes. Good luck.